Mathematical biology is also known as biomathematics, is an emerging dynamic field of applied mathematics providing an interdisciplinary subjects containing a large number of problems in biology like population dynamics, biomechanics, genetics, epidemiology, and so on. This considers only those problems which are possible to be mathematized. What is mathematical modeling or modeling process? A mathematical modeling is a set of assumptions about some system like biological, etc., which can be expressed mathematically. Mathematical reasonings or computations are then used to generate predictions for that system. In other words, mathematical modeling is the activity by which a problem involving a real world is translated into a mathematics to form a model which can then be used to provide information about the original real problem. Different techniques for modeling process. First, classical techniques. Here we use the different mathematical methods like differential equation, integral equation, difference equation, matrix theory, graph theory, and so on. Statistical methods consider a sample of all possible observations and put up a hypothesis about the population, and then we use the statistical theory and test of significance. Computer simulation technique. Computer simulation is the process of mathematical modeling performed on computer, which is designed to predict the behaviors or of outcome of a real world or physical system. Operation research. This is the method of analysis by management receives for their receives aid for their decisions when optimization and control problems, assignment problem, TSP, transport, TSP, and is the TP, TSP, AP. This is the game theory. Modern mathematical techniques. There are so many techniques in modern mathematics like fuzzy sets, topology, geometry, the modern mathematical techniques. Describe dynamic modeling. Dynamic modeling of a system is a mathematical system of the laws about the changes of states of the system. A dynamical model may be either deterministic or stochastic and discrete time or continuous time. Deterministic model. In deterministic model, the future of the system can be predicted if its present conditions are known. Here we have to choose some quantities called the state variables, which involve a balance of biological realism and mathematical complexity. For examples, individuals are age, sex, and psychological variables, etc. Populations are living organisms. Communities are individual of each interacting species, etc. Modeling in discrete time. Suppose x suffix t small t and x suffix t plus delta t denotes the state variables of the system at time t and t plus delta t respectively. The x t plus delta t is a function of xt, that is x t plus delta t is equal to function of xt, where f depends on the system under consideration. And on the other hand, if f depends on both xt and explicitly time t, then this is the expression f of xt comma t, and it is a non-autonomous system difference equation. And it is to be noted that the discrete time model forecasts the states of system at series of equally spaced times. Modeling for continuous time. Here the values of state variables are to be predicted in future time, and so we need to consider the rate of change of the state variable x with respect to time t. Thus for autonomous system, the equation is dx dt is equal to some function x fx, while for non-autonomous system dx dt is equal to f of x and t. And stochastic models, in this model, the state of a system at a future time can be predicted exactly from its present state. Unpredictability enters in biological system in various ways. Since random fluctuations are inherent in animal populations and in their environment, it is desirable to incorporate chance variation as an integral component of the model. Discuss about the exponential and Malthusian population model. Very important model uh, for first year, for first time, the exponential model or Malthusian model, population model. This is a single species continuous time model. Single species continuous time model. Suppose the individuals in a population grow independently in a finite region, and there is no competition amongst themselves, and there is no migration. This is an important condition: no migration or immigration. No immigration or migration. No immigration or migration. And the population changes due to births and deaths only. So only changes population due to the births and deaths only. No migration and no immigration. No output or input from outside. Suppose at time t, the population size in a region be capital N suffix t. T is a time variable, nt, population size, is a non-negative integer. While is supposed, because this is the size, population size, number of species here, so nt is a non-negative integer which is supposed to be continuous and continuously differentiable everywhere within it. Consider time interval t comma t plus h. This closed time interval, let the birth rate and death rate be beta and delta respectively. Then the change in the population of the species between the times t and t plus h is given by nt plus h minus nt is equal to beta into nt into h minus delta into nt into h. This is the birth rate. This is the birth rate beta. Nt is the number of population. So in time h, length is the time interval h. So this is the t, and this is the time interval t, and this is the t plus h. So after time h, this is the time h. After time h, this is the total birth in the this is the time interval h time interval, and this is the death rate delta. So this is minus of total death. So this is the population at the time t plus h minus the at the time t. So this is the called is the alpha in t into h, where alpha is the beta minus delta. Alpha is the beta minus delta, and this is the birth rate, and this is the death rate, and this is called the growth rate. This alpha is called the growth rate. Taking so dividing by h on both sides, we get nth minus nta by divided by whole divided by h is equal to alpha into nt. So taking the limit h tends to 0, we get a limit h tends to 0, nt plus h minus nt by h is equal to alpha into nt. So this is the from the differential calculus, this is equal to dn dt, ddt of n. This is the ddt operator, differential operator. So ddt n is equal to alpha n. This is the important equation, very much important equation. This is the exponential or Malthus model of population growth. This equation is known as the exponential or Malthus model of population growth. Now, to solve this model, this ordinary differential equation 2.2, this is the ordinary differential separable, and so for n not is equal to 0, and this separation of variable, so integration dn by n equal to alpha into integration dt plus some constant integrating constant c dash. So log n equal to alpha t plus c, where c is an arbitrary constant. So suppose call it c dash. So call it c dash. So c dash is here arbitrary constant. Using this initial condition, n at the point 0, time 0 is called n0, the initial population size. So initial time when t is equal to 0, this is the called it n suffix 0, n0. We get, so put here at the time t is equal to 0, so n equal to n0. So we get log n0 is equal to some c plus 0 plus c dash. So c dash is equal to this. So put here log n plus equal to alpha t plus log n0, value of c dash. So dividing this minus log n minus log n0. So log n by n0 equal to alpha t, and hence n by n0 is equal to e to the power alpha t, that is n is equal to n0 e to the power alpha t. This is the solution of the differential equation 2.2. So this is the solution, Malthus solution, exponential solution. And this solution 2.4 depends on two parameters. Number one parameter is alpha. This is the growth rate. Growth rate means this is the beta minus delta, birth rate minus death rate. This is called growth rate. So this is the growth rate. And second, the initial population size n0. So this is the alpha. One parameter is alpha, growth rate, and second parameter is the n0. n0 is the initial population size. This is called n0. Now, if we draw the curve, draw the solution curve 2.4 for 2.4, if assume here n0 is constant, suppose n0 is constant, so we get for any alpha, for positive alpha, you get the curve, solution curve is this type. When n0 fixed and alpha greater than 0, so is the exponential growth. This is called the exponential growth when n0 fixed. When n0 fixed, here n0 is value of this n0. This is the axis n axis, and this is the time axis t. X axis, along the x axis this time axis t, and the y axis the total population size capital N. And when alpha is negative, the exponential decay, and the solution curve is this type, exponential decay. When t tends to infinity, and this the population size is decaying ultimately and vanishes sometime. So this is the Malthusian model or exponential model. So first establish the equation 2.2, the exponential model, establish the and then find the solution of this model, and this is the graph of this model. Now here a problem. The estimated population of the world in 1961 was 3.06 billion, that is 3.06 into 10 to the power 9, and growth rate was estimated by 2% per annum. Use the exponential model to estimate the current population in the year 2020, suppose. So in 1961 is this 3.06 billion, so call it n0. 3.06 into 10 to the power 9. For exponential model, we have n equal to n0 e to the power alpha t. So here n0 is equal to this, and alpha is equal to 2% per annum. So 2% means 2 by 100 per annum per year. So 0.02 per year. So here in the year 2020, and t is equal to length of the time interval 2020 minus 1961, that is 59 years. Length of the time, that is the t, length of the time interval. So so n at the time interval 59 years, after 59 years, so this n0 into exponential e to the power alpha equal to 0.02 into t here 59 years. So this equal to 9.96 into 10 to the power 9, this. So this is the by this exponential model, the population in the year 2020 here this. But actual population here 7.8 billion, that is 7.8 into 10 to the power 9. So by this model we get an overestimate because actual population is 7.8 billion, but here 9.96 billion. So due to the fact that the growth rate has not been constant, here we assume growth rate is constant, but actually in the real field growth rate is not constant. Rather, it has been falling since 1961 until present. So it is the one of the defect of this Malthus model. The growth rate is constant, but in the real field growth rate not always is constant. So by this model we estimate the actual population in 2020 is 9.96 billion, but actual Actually, there is 7.8 billions. Now write down the Malthus model in terms of difference equation. So change the population in is given by nt plus 1 in replace h by 1. So t plus 1 minus nt is equal to beta nt minus delta nt. Here assumed h is equal to 1. So this called is delta n. So beta minus delta into n, beta minus delta equal to n, and this called is alpha. So delta n is equal to alpha into n. It's 2.5. Also nt plus 1 minus nt equal to nt plus 1 is the nt plus 1 is equal to n suffix t plus 1. Nt is equal to beta nt minus delta nt. That is nt plus 1 is equal to 1 minus beta minus delta nt. This is called lambda. So lambda is equal to 1 plus beta minus delta. So lambda is equal to 1 plus alpha. This lambda is the finite growth rate of the population, called the finite growth rate of the population. Now 2.5 equation, 2.5 difference equation, 2.5 and 2.6 are mathematically equivalent, and both of them represent the Malthus model of population growth. The difference equation 2.6 is linear. Difference equation 2.6 is linear. This is the equation, linear difference equation, and so the model is linear. But this linear model produces exponential growth or decay. It is not linear, produces exponential growth. Exponential means not linear, it will give us something. So the equations 2.6 can also be described by this: nt plus 1 is equal to lambda nt. This can be replaced by t, this is equal to nt, t plus 1 replaced by t. So nt is equal to lambda into nt minus 1. So nt is equal to lambda into nt minus 1. Now we have some MCQ. The model nt is equal to lambda nt minus 1 and delta n is equal to alpha n represents growing populations when lambda is any number in the range 1 and when alpha is any number in the range 2. You have to determine the value of this value 1 I and this value 2. Nt is equal to lambda into nt minus 1 and delta n is equal to alpha n represents a growing population when lambda is any number and the range of, you have to find the in 1 you have to find the value of lambda, range of the lambda, and in 2 we have to find the value of alpha, where alpha is given by this, alpha is equal to given by beta minus delta, and lambda is given by 1 plus alpha, and the finite growth rate of the population. So alternative A alternative, lambda greater than 1, alpha less than 0, and so on. These ABCD 4 alternatives here. Now here there is the growing population. For this growing population, lambda is equal to 1 plus alpha. For growing population, alpha obviously greater than 0. Alpha is means the growth rate, alpha is the beta minus delta. So alpha obviously greater than 0. Alpha is obviously greater than 0. And when alpha is greater than 0, so alpha plus 1 is greater than 1. So when lambda is greater than 1 and alpha is greater than 0, so only possible when D is the possible answer, correct answer. Next question, model nt equal to lambda nt minus 1 and delta n equal to alpha n represents decline population. So here lambda is any number ranges from this and alpha is any number ranges from this. So decline population, this means here lambda, alpha is negative, so alpha is negative, alpha is less than 0. So alpha is less than 0, alpha is less than 0. This is the this alpha is less than 0 means that lambda is less than 1. Lambda is less than 1, alpha less than 0. So 1 plus alpha is less than 1, alpha is less than 0. So 1 plus alpha is less than 1. So 1 plus alpha is lambda. So lambda is less than 1. So on the correct answer is B. Lambda is less than 1, alpha is less than 0 when decaying population. And next problem, same problem, only about stable population. Stable population where when lambda alpha equal to 0, the equal death rate and birth rate are equal. So alpha equal to 0. So alpha equal to 0, alpha means alpha, lambda is equal to 1 plus alpha, alpha equal to 0. So when lambda is equal to 1. So answer is this, when correct answer is B, that is range of lambda is equal to 1, value of lambda is 1 and alpha is the 0. A model is said to have a steady state or equilibrium point at n star if whenever nt equal to n star and then nt plus 1 equal to n star. Actually, rephrase this definition as a model is said to have steady state at n star if whenever n equal to n star, then delta n equal to this. Here we use here a definition, steady state model, steady state or equilibrium point at n star, equilibrium point. So nt definition is this: if whenever nt is equal to n star and nt plus 1 is also n star, same value. So a model is said to have a steady state at n star if whenever n equal to n star, the delta n is equal to n star, delta n equal to 1, delta n equal to 0, and none of these. Actually, delta n means alpha into n. Delta n means alpha into n. Already have this 2.5 in equation, delta n equal to alpha n. So delta n equal to, here delta n means nt plus 1 minus nt. So delta n equal to this, delta n equal to n equal to 0 when alpha equal to 0 for steady state. Now delta n equal to nt plus 1 minus nt. Now nt plus 1 equal to n star by this problem for steady state equilibrium state. So and nt is also n star value, so this is equal to 0. So correct answer is delta n equal to 0. This is the steady state when delta n equal to 0. Suppose next problem, a population is described by a model nt plus 1 equal to 1.5 nt and n5 equal to 7.3. Find nt for t is equal to 0, 1, 2, 3, 4. nt plus 1 equal to this, n5 equal to this. So it's a simple problem. You have to find the solution of a difference equation nt plus 1 equal to 1.5 nt. When t is equal to 4, so from this relation n4 plus 1 is equal to 1.5 n4, that is equal to n5 equal to 1.5 n4. Now the n5 value of n5 is 7.3, so put the value of n5 is 7.3, so n4 equal to 7.3 by 1.5 and this is the 4.87. So n4 is equal to this, and recurrently put n equal to 3, n equal to 2, n equal to 1 and n equal to 0, we get the result n0, n1, n2, n3 and n4, and similarly. What are the defects of the Malthus model? The Malthus model predicts that population growth will be exponential. However, such a prediction cannot really be accurate for very long. After all, exponential functions grow quickly and without bound. And according to such model, sooner or later, there will be more organisms than the number of atoms in a universe. So for this exponential growing, so after some time, more organism than the number of atoms in the universe. This is impossible. Number of atoms more organism than the number of atoms in the universe. Some time after some time, some organism is the number of atoms more than number of atoms in the universe. The main flaw is that we have assumed the fecundity, that means growth rate, and death rates for our population are the same regardless of the size of the population. We have assumed the growth rate and death rate for our population are the same. It is the main flaw of this size, regardless of the size of the population. But actually, it is not whole. Regardless of this growth rate and death rate are same for our population are same. Whatever the size of the population, but it is not true. In fact, when a population gets large, it might be more reasonable to expect a higher death rate and lower fecundity. And combining these factors, we could say that as the population size increases, the finite growth rate depends on the size of the population. So growth rate should be density dependent. Actually means population density dependent function, not same for the all population regardless same size or regardless of the size of the population, not same. So it is the main flaw of this Malthus law is that model is they assume the growth rate and death rate for the same regardless of the size of the population, but actually it depends on the density of the population. Growth rate depends on the density of the population. Now come to the logistic model, second model in the biomathematics, logistic model. The scientist Varals proposed that a self-limiting process should operate when a population becomes too large. He suggested this model is this: dndt is equal to alpha n bracket 1 minus n by k. Here alpha and k are the positive constants, and this is known as the logistic growth model of population. Logistic growth model, not exponential, logistic growth model or Varhulst model, logistic growth model in the population. And this is the model dndt. N is the density of the population size of the some single species, is alpha into n 1 minus n by k. Nt is the population of the species at time t, and alpha is a function of n. Here alpha into 1 minus n by k, alpha n equal to this, alpha into 1 minus n by k. So this result can be written as is equal to alpha into this, alpha into 1 minus n by k. So alpha is a function of n into n. So dndt is equal to alpha n into n. So here in exponential model we assumed here is the dndt is equal to alpha n is the exponential model. Dndt is equal to alpha n is some constant. But in the logistic growth model we assume this alpha is not constant. This we assumed here this equal to alpha is some function of n into n. The basic difference between the exponential model and logistic model, logistic growth model. Here exponential model or Malthus model, here alpha is constant. Here logistic growth model, here alpha is a function of n, and value of alpha n equal to alpha into 1 minus n by k. K is some constant. We have to, later we determine this value of this. So alpha is equal to, here this alpha same, this alpha and this alpha is same, this alpha same. So here alpha into some n, here alpha is into 1 minus n by k in the logistic growth model. This alpha n into n, where alpha n is given by alpha into 1 minus n by k. This alpha n is equal to this, and this is known as the per capita birth rate or actual growth rate. So alpha n from this relation here, dndt is equal to alpha n into n. This alpha n means alpha into 1 minus n by k. So alpha n equal to from this relation alpha n equal to dndt by n, So this alpha n dndt by n, this alpha n means dndt by n. This is known as the per capita birth rate or actual growth rate. This depends on the n. Alpha is the some positive constant. This alpha is same as the exponential model. This alpha is constant, some constant. This alpha is constant. But this alpha in this alpha is not same. This alpha is dependent on n and this alpha is constant. It's called linear growth rate. This alpha is called linear growth rate. This alpha is called linear growth rate. Linear growth rate. and this alpha n is called per capita growth rate or birth rate. The constant k is called the carrying capacity of the environment. This capital K is called the carrying capacity of the environment. The maximum possible population. Carrying capacity means maximum possible population. This is the maximum possible population, which is usually determined by the available sustaining resources. The maximum possible population is called the carrying capacity of the environment. And in this model, like the Malthus model, the only mechanism for changing the population size are births and deaths. And there is nothing to account for migration into or out of the population. No immigration, no migration. Output or input. No output, no input on the population. Here we assume this as we assume here Malthus model. This is the exponential growth model and proposed by the Verhulst. Scientist Verhulst proposed this. Describe the condition when the logistic growth model approaches to the corresponding exponential model, Malthus model. So, logistic growth model tends to Malthus model depending on some conditions. First condition, when carrying capacity K tends to infinity. Carrying capacity K tends to infinity. So, actual growth rate alpha n is equal to alpha into 1 minus n by k. So, k tends to infinity. So, this tends to 0. So, this tends to alpha. Alpha is the constant, is the linear growth rate. This alpha is used here the exponential model, Malthus model. So, when carrying capacity is going to infinity. Carrying capacity means the maximum population, maximum possible population going to infinity. There is no upper limit. So then exponential logistic growth model tends to Malthus model, exponential model. The linear growth rate alpha. So the actual growth rate tends to linear growth rate. This means that alpha is the growth rate for the corresponding exponential model in which the resources are infinite, and this is the reason for its name logistic growth rate, and this is the reason for the name logistic growth rate. And when k tends to infinity, alpha n tends to alpha. Alpha is the linear growth rate and alpha n is the actual growth rate. Next condition, if for small n compared to k, the actual growth rate alpha n tends to alpha, and this is consistent with the fact that when the population is small, very small population, the resources are plentiful and seemingly infinite. It is only when the population size gets larger that the effect of the fitness of the resources are noticeable. Thus, when k tends to infinity or n is very small, so here when n is very small, here n is very small. So when n is very small, so n by k is tends to 0. So then alpha n is equal to alpha. So either k tends to infinity or n is very small. N is very small. So second condition is very small. So population density is very small. Population size is very small. The n for small n, the actual growth rate alpha n tends to alpha. This is consistent with that the population size is small. N is very small, and this is certain. And then dn dt is equal to alpha n, and this is the exponential model. So by these two conditions, carrying capacity k tends to infinity or the population size n is very small, then the exponential, then the logistic growth model means this logistic growth model tends to the exponential model, that is Malthus model. Find the equilibrium points and the linearization about each for the logistic model. Hence, determine the stability of each of these equilibrium points. Find the equilibrium points and linearization for this logistic model, logistic growth model. Here, dn dt is equal to, suppose say fn. Fn means alpha into 1 minus n by k into n. this is Fn, called it Fn, and this is equal to alpha n minus alpha by k into n square. Now Fn that is equal to dn dt is equal to 0. So when dn dt is equal to 0, so either n equal to 0 or 1 minus n by k equal to 0, that is n equal to k. So when dn dt is equal to 0, so either n is equal to 0 or n equal to k. So the equilibrium points are n equal to 0 and n equal to k. So n equal to 0, n equal to k are called equilibrium points. Why? Because dn dt equal to 0 implies this. So dn dt equal to 0 implies this, n is equal to 0 or n equal to k. Now find the f dash n. So f dash n equal to, from this, f dash n equal to this alpha is constant, minus, and this equal to twice alpha by k into 2n. So taking common alpha, we get 1 minus 2n by k. Now here n equal to 0 and n equal to k, two equilibrium points. So put f dash 0 in place of n, put 0. So this is equal to alpha into n equal to 0. So this is equal to alpha. F dash 0 is equal to alpha. And put k in place of n. So in place of n, put k. So k by k equal to 1. So 1 minus 2, that is equal to minus alpha. So f dash at the point n equal to 0 is equal to alpha. F dash at the point n equal to k is equal to minus alpha. So the linearization about n equal to 0, this dn tilde dt is equal to alpha n tilde. Here n tilde, we note that n minus ne means equilibrium point, at n value of n at the equilibrium point. Here n minus 0 for the when n equal to 0, for when n equal to 0, so put n equal to 0, so n tilde equal to n, and so linearization model is this, about n0 is equal to this. And when n equal to k, then linearization model is dn tilde dt is equal to minus alpha n tilde. Here n tilde means n minus ne, n tilde n minus ne means k at the point k, n equal to k. So this k, so this equal to alpha minus dn dt is equal to, because f dash k is equal to minus alpha, so dn tilde dt is equal to minus alpha into n tilde. Since alpha is positive quantity, linear growth constant, so this positive constant, positive value, so n is equal to 0 is unstable, and n is equal to k is asymptotically stable. N is equal to 0, unstable, for alpha equal to greater than 0. So for this, plot the logistic model, logistic growth model, dn dt, put here along the y-axis dn dt, along the x-axis n dn dt, put here logistic model, we get the plot here. So when alpha greater than 0, at n is equal to 0, for alpha n is equal to 0, the this is the tend to be this and this, and unstable. So this point O is unstable point, and this point K is here K asymptotically stable. For small part operation, n tilde is equal to nt minus ne, and dn dt is equal to fn n tilde ne, and this is the ne plus n tilde f dash ne. Calculation for this Taylor extension, this is n tilde ne, because fn is equal to 0, so dn dt is equal to dn means n tilde plus ne, so this dn equal to n tilde f dash ne. And linearizing about, so now dn is equal to n tilde f dash ne, so dn tilde is equal to this n tilde is equal to this is a constant, n is equal to constant, so dn tilde dt is equal to n tilde f dash ne. Linearization fact this. So at the point k is the here the asymptotically stable. If we draw the curve for dn dt, and the value of this dn dt, value of after simplification, if you get this result dn dt, plot this, and you get this asymptotically stable. And derive the solution for the logistic model, and hence draw the logistic curves. So logistic model, equation, differential equation is this: dn dt is equal to alpha in 1 minus n by k, and k dn dt is equal to, after simplification we get this result, and k dn n k minus n is equal to alpha dt. K n k by n divide on both sides and get this result. Hence, to be noted that this equation 1 has two particular solutions: n t is equal to 0 and n t equal to k for all t, corresponding the equilibrium points. Integrating these two, we get this, and after this simplification, we get log of mod of n by k minus n equal to alpha t plus c, that is mod of n by k minus n equal to the power alpha t plus c. Using the initial condition n0 is equal to n0, the initial population size we get n0 by k minus n0 is equal to the power alpha 0 plus c to the power alpha c. So put the value of e to the power alpha c in 3, we get the result a mod of n by k minus n is equal to n0 by k minus n0 to the power alpha t. Since n0 not is equal to 0 or not equal to k, so neither n nor k minus n can change a sign on an orbit, and hence the sign n by k minus n is the same for all t. Thus n by k minus n is equal to, so we remove the modulus sign. So n0 by k minus n0 is equal to the power alpha t is equal to p, say. So n equal to kp minus np, that is n common bracket 1 minus p 1 plus p is equal to kp, that is n is equal to kp by 1 plus p, and put the value of p, you get the result n is equal to this, and hence the solution for the logistic growth model is k n0 by k minus n0 to the power minus alpha t plus n0. Notice that this solution includes the solution nt is equal to 0 taking n0 is equal to 0, and nt equal to k taking n0 is equal to k. When put this n0, when put n0 is equal to 0, put here n0 equal to 0, then n is equal to 0. If you put n0 is equal to k, n0 is equal to k, so this term is 0, n0 is equal to k, so this is equal to 0, and n0 is equal to k square and k, and this is equal to nt equal to k. So these solutions depends on three parameters: initial population n0, linear growth rate alpha, and k is the carrying capacity. So this solution depends on three parameters: n0 initial population, k carrying capacity, and alpha is the linear growth rate. Now we can draw the figures for the solution 5. Which shows the effects of varying each of these parameters with the other fixed. These curves are known as logistic curves. This curve is known as logistic curves, and this is the graph for this. It is the k, nt, and time t. If we draw this horizontal line at the point k is the carrying capacity. If we choose n0 here, then the n0 here near the origin, so graph is this type. This is the asymptote, this line, horizontal line. And if n0 is this, if value of n0 is this point, from this point, so graph is this. If n0 value of n0 is the above the carrying capacity, initial population, so graph is this. So graph is decaying. Logistic population growth rate, logistic curves for different n0. From the above figure, if n0 is less than k, nt simply increases monotonically to k, while if n0 greater than k, then it decreases monotonically to k. In the former case, there is a quality difference depending on whether n0 greater than k by 2 or n0 less than k by 2. With n0 less than k by 2, this is k, so k by 2 is this point, k by 2. If n0 is less than k by 2, this, and n0 is greater than k by 2, that is this point n0, so we form a typical sigmoid character which is commonly observed when n0 is less than k by 2. This is the sigmoid character. Next problem by this model, logistic growth model. A population of protozoa is being studied. From the observation made over the first day, the growth rate is estimated to be 231% per day. After 6 days, the population was observed to saturate at 375 cells. Find the logistic curve which models this population growth. The initial population size is 5. So initial population 5 means n0 equal to 5. Here alpha, the linear growth rate is 231%, that is 2.31, and the carrying capacity is this 375 cells saturated this point, these cells. So carrying capacity capital K is equal to this. Now the solution for the logistic growth model, nt is equal to k n0 k minus n0 e to the power minus alpha t plus n0. So put these values, all the values, and get the result nt equal to this. And for rough sketch of this solution is shown in the following figures. This is the carrying capacity 375, this is the nt along the y-axis, along the x-axis this t, and the first day, second day up to 6th day. So n0 is equal to n0 here, n0 equal to 5. So starting from the n0, and this is the k, value of k. So this is the sigmoid curve, logistic curve of this. So today class up to this.